Good morning, students. Today we will see carrier concentration in P-type semiconductors. I am Dr. R. Priya, Professor of Physics, RMD Engineering College. So look at the picture. This is showing the formation of P-type semiconductor. So you know intrinsic semiconductor, which is a pure form of semiconductor, can be imagined to have only silicon atoms in which the dopant, that is trivalent dopant. One example is taken as aluminium, whose atomic number is 13. So if you write its electronic configuration, it will be 1s2, 2s2, 2p6, 3s2, 3p1. So the outermost shell will have 3 valence electrons. So it is a trivalent impurity. Now this is introduced into the intrinsic material. So its rearranged bond formation structure is shown in the picture. So you can see 3, 1, 2 and 3 valence electrons, which are once again forming the covalent bond with that of the silicon neighboring atoms, and on the fourth side you are having a vacancy which is ready to accept an electron from some other place. So every impurity is responsible for creating such a kind of vacancy. Now this will be filled by some electron from some other position, creating a hole there. So every impurity atom is responsible for creating a hole. So thereby making holes to be the majority carriers and electrons to be the minority carriers. Now coming to this picture, the first one is showing the N-type semiconductor. So here you are able to see a pentavalent impurity, and all 4 valence electrons are involved in the formation of bond, and 1 electron is free. So this impurity is ready to donate 1 electron to the system. And this is P-type semiconductor. Here once again boron is taken, but germanium is assumed. So both germanium and silicon are tetravalent. So no difference in the bond structure. So you can see hole being created because of the impurity, that is trivalent impurity. Now coming to the energy band diagram, for the N-type semiconductor, valence band, conduction band, and all these impurity will have a donor level. That donor level will be formed very close to the conduction band. This is for the case of N-type semiconductor. Now coming to the P-type semiconductor, you are having valence band, conduction band, and there are many LFG levels which are ready to accept the electrons, which means they form the acceptor level which are close to the valence band. So that is the explanation of this picture. So I have drawn the energy band diagram. I have shown valence band, conduction band, acceptor energy level. Now I am showing the EF also, which will lie in between EA and EV. Now I have to find out the carrier concentration. Carrier concentration is majority carrier concentration, which means holes. Okay, so I will not count the acceptor impurities. Instead, I will be counting the empty holes available in the valence band. So all those are transferred to acceptor. The acceptor impurity have accepted the electrons. That is the meaning for it. Okay, so I will write an expression for NH. So where from I will write the expression for NH means I will write it from the intrinsic carrier concentration, that is density of holes in the valence band. So that is the starting point for us. So let me write the expression. NH is equal to 2 into 2 pi mH star kBT divided by H square whole power 3 by 2 exponential EV minus EF divided by kBT. Okay, so let me consider NA to be the number of acceptor energy levels centimeter cube, which means per unit volume. That's the meaning. Then let me write the general equation, that is electron density in the acceptor energy level. So you know the basic equation, same equation only, instead of n of E, I am just giving it as n of EA. Okay, dE is equal to Ez of EA F of EA then dE. So in this I can write this as, in general this one will become NE is equal to NA F of EA. So I will write F of EA is given by 1 divided by 1 plus exponential E minus EF. No, so that has to be replaced by EA minus EF divided by KBT. Okay, this is, let me write this as first equation. This is second equation. This is third equation, or let me give this as third equation. And this as fourth equation. So here you know EA minus EF, you see the picture, EA minus EF by KBT is positive because EF is lying in between EA and EV. So EA minus EF is positive, which means this ratio will be much greater than 1. So which means what I can say, you look into the F of E equation, exponential of EA minus EF by KBT will be much greater than 1, and so 1 can be neglected. So what will happen to F of EA equation? Will become 1 divided by exponential EA minus EF by KBT. So I will write this as exponential EF minus EA by KBT. Okay, so this is equation number 5. Now, as how we have done the N-type semiconductor derivation at equilibrium. At equilibrium, what? The number of holes in the valence band is equal to the number of electrons in the acceptor energy level. So simply speaking, it is something like this. Hole density is equal to electron density. Okay, the location is different, that's all. That is number of holes in the valence band as a holes density. Then number of electrons in the acceptor energy level, that only is electron density. Okay. So let me write the equation 2 into 2 pi mh star KBT divided by h square exponential EV minus EF divided by KBT is equal to NA divided by exponential EA minus EF divided by KBT. So I will bring all the exponential to one side. So exponential, I will take commonly the denominator to be KBT, EV minus EF. Then what will happen to this denominator? It will come to the numerator and will get added along with the numerator. Correct? So plus EA minus EF is equal to NA divided by 2 into 2 pi MH star KBT divided by 3 by 2. I missed here whole power 3 by 2. Okay, so whole power 3 by 2. So simplify this. Exponential denominator KBT, EV, I write EA and then add EF and EF, that is minus EF will become minus 2EF is equal to NA divided by 2 into 2 pi MH star KBT divided by H square whole power 3 by 2. Now I have to find out first EF, which is inside the exponential. So what should I do? I have to take ln on both sides. So taking ln on both sides. So ln exponential, they will get cancelled. Only the terms present inside the bracket will come. So it is EV plus EA minus 2EF divided by KBT is equal to NA divided by 2 pi MH star KBT divided by H square whole power 3 by 2. Okay. EV plus EA minus 2EF. I retain that along this side. I bring the denominator to, that is the KBT, to the other side. So KBT ln NA whole divided by 2 into 2 pi MH star KBT divided by H square whole power 3 by 2. Then I will retain only 2EF one side and bring rest of the terms to the other side. So what will happen? That is, I am taking 2EF to the other side, so it will become plus 2EF, and write the rest of the terms in such a way that EV plus EA then minus KBT ln NA divided by 2 into 2 pi MH star KBT divided by H square whole power 3 by 2. Then I will write EF is equal to EV plus EA divided by 2 minus KBT by 2 into ln NA divided by 2 into 2 pi MH star KBT divided by H square whole power 3 by 2. Okay, so this is the expression for Fermi energy. Okay, now to write this in a simplified form, I simply assume, okay, because we have to find out Fermi energy perfectly, which means the temperature has to be as low as possible. In fact, it has to be at absolute zero. Okay, so at T is equal to 0 Kelvin, EF is equal to EV plus EA by 2. So, in the energy band diagram which we have drawn, so we have shown the conduction band, we have shown the valence band, and we have shown the acceptor energy level. So this represents EV, and this is EC, and this is EA. Now I have to locate EF. EF will be exactly in between EA and when. Here you should put at T is equal to 0 Kelvin. Okay. So I will stop with this in this video and continue taking this EF equation and substituting the expression in the density of holes in the valence band. I will find out. Okay, that is in the continuation in the next video. Okay, thank you. So I have stopped this with calculation of Fermi energy. I will continue to calculate carrier concentration in my next video. Okay, thank you students.